Hello, my name is Natasha Sharygina. I'm a professor of computer science at the University of Lugano, Switzerland. I'm going to talk about SMT-streamlined software model checking. Software model checking has been a focus of my research for a number of years. Roughly 15 years ago, I established a formal verification and security lab in Lugano after moving there from Carnegie Mellon University when I received the career award. Since then, in the lab, we developed a lot of model checking tools, program analysis tools, which allow fully automated program analysis. I'm not going to talk about all of them, but everybody is very much welcome to check our website and see descriptions for each of the projects we conducted ever since. I'm going to talk only about two tools. And before I start describing them, I would like to give a brief overview of our work in Lugano. It will help me to justify our solutions and explain on a high level what is our unique approach. The focus of our work is program verification. We're using software model checking. And the tools which have been already developed are UpProven, HighFrog, FunFrog, RollCheck, LoopFrog. They all share the same fundamental concept that program verification should be incremental if we want to make sure it's practical. In parallel, we have another track on the development of efficient decision procedures as computational engines of verification, both at the SAT and SMT level. What is unique in our group is that these two tracks are not independent. They're really coupled. They are interlinked. Whenever we're developing new algorithms for program verification, we see how computational engines, SAT or SMT solvers, can help us to come up with the better solution. And the same is true about the development of new decision procedures. They're very often customized with respect to a particular verification task, which is needed for program verification. The other essential track is on the construction of automatic symbolic abstractions, which are essential components of modern program verification. Without the abstraction, practical analysis is not possible. Abstraction allows us to remove unnecessary details of the system in order to focus on what's important for the verification of the program. We are using Craig interpolation as one of the main concepts for automatic construction of symbolic representations of the system. In particular, we have a very useful concept which we call function symbolization, which enables efficient incremental program analysis. Every time when it comes to using the abstraction, as most of you probably already know, the abstraction might introduce spurious behaviors in the system description. For that, a refinement technology is needed to remove the spurious behaviors. We have a number of solutions there, which we call theory refinement and summary refinement. Our decision procedures track is really focuses on the integration with verifiers. How can we integrate properly, not just being used as a black box? We need the solver which we can access in a full manner and know it perfectly well so we can adjust and adapt it. We are developing our own SMT solver called OpenSMT, which combines the state-of-the-art MiniSat2 SAT solver with a number of state-of-the-art decision procedures for various first-order logic theories. It's incremental. It's a nice feature which enables efficient verification, incremental verification. It's interpolating solver, and we enhanced it with a number of decision procedures for the construction of interpolants. Not only is a collection of various decision procedures for the interpolation, but we have a flexible interpolation framework which allows us to adjust the size and the strength of the constructed interpolants. Our solver is open source. We welcome collaboration. We welcome people using our tool and contributing modules to it or giving us feedback on the performance of our developments. It's parallelized. It comes with efficient search space partitioning, which makes it very handy when it comes to large systems. And it is efficient. We compete with other SMT solvers. We participate in SMT competition every year, and occasionally our tool comes with some awards of winning or being runner-up for various tracks in the competition. One of the recent editions is a proof production, when the solver produces certificates demonstrating that the solver is doing a sound and correct job, which is essential since the solver is used as the engine of verification. And as I said, it's really tightly coupled and integrated in the model checking projects, not only in our group, but in some other academic and industrial establishments. Naturally, it's a team effort. A lot of people have been involved in the development of these technological solutions. Most of them are PhD students who are doing PhD studies with us. Many of the students already graduated and work in some companies such as Facebook, Amazon, Ethereum, and other places, some of them even professors. What I would like to point out that two students, current PhD students in our group, Sepide Asadi and Martin Blicha, who are active developers and researchers in the field of program verification, are going to be our assistants in this summer school. You will meet them when we are preparing and working with you in the lab sessions. In this summer school, I'm going to talk about two projects, HighFrog and Approva. They both share a lot of fundamental concepts for incremental program analysis. They both bounded model checkers, which use SAT and SMT for program encoding and for reasoning about the correctness of software. They both use symbolic abstractions called function summaries, which are computed based on Craig interpolation. Both tools come with different levels of encoding, starting from Boolean encoding and going into SMT encoding with using different theories of different complexity. It provides ability to create compact and readable summaries, which could be efficiently used in incremental analysis. They exploit the capabilities provided by our SMT solver of flexible interpolation, because very often we need to adjust the size and strength of interpolants, the abstractions which are used for program verification. The major difference between these two projects is that HighFrog is a tool which is designed for verification of a single system when it comes to verifying different properties, different specifications, which is a very common task. You have a system and it comes with a lot of specifications to be checked. Approva, in contrast, actually focuses on verification of different systems, which perhaps closely related, like system upgrades or bug fixes, but you are going to verify the same property. Whenever system gets updated, you want to make sure that the previously verified properties still hold. I will go and present the technical background behind both of these tools. I will start with some basic fundamentals of model checking, just to make sure that everybody is up to speed with the technology behind our tools. And later, I will move gradually into more advanced topics, demonstrating how exactly our solutions are enabled to be efficient. The background of our tools is bounded model checking. We look only for bugs up to a specific depth. This seems like a restriction, but it makes it really very practical. The depth of verification could be quite deep, quite large. We can still catch a lot of bugs with this approach. The program is encoded into symbolic formula, which is called the BMC formula, which is then given to a solver, SAT or SMT solver, and which is being checked. This satisfiability check by SAT or SMT procedure corresponds to finding an error in the system. If the solver returns SAT, it means the error is reachable. We detected the bug, and the satisfying assignment, which is produced by the solver, actually is an error trace, which could be used to trace the origin of the bug. If the system returns unsat, if the solver returns unsat, it means the error is not reachable, so the program is safe. I will talk in more details about this concept. You will understand how it all works together. Altogether, this is an algorithmic, logic-based verification. You start from a program, you need to verify to see if it's correct or not, and you specify some safety properties. For example, that you never write outside of a particular bound, that the memory is never allocated outside of allocated space. And then the program, together with safety properties, is encoded into a logical representation. We call it a verification condition, which needs to be checked. The check is done by the corresponding decision procedure to the logical encoding which you created while modeling the program together with the properties. For each decision procedure, you will have a solver for the corresponding logic, which is going to say yes or no. And it means that the system is safe or not safe. As already said, the essence of the logic-based verification is the use of the corresponding solver for a particular logic being used. The common techniques which are used in program verification are SAT-based and SMT encoding. Why are they so popular? One of the reasons is because these technologies, SAT solving and SMT solving, are highly investigated by a large group of scientists. And there is the annual competitions both for SAT and SMT, while people trying to come up the most efficient tools to solve as many problems as possible. Here's a slide from Moshe Vardi, which demonstrates, for example, how between 2000 and 2012, the efficiency of the best solver got improved. The best solver in 2012 is 1,000 times faster than the best solver in 2000. Here's the similar statistics from the competition of SMT solving. And you can see that, for example, the total time for solving a particular benchmark, in this case, quantify-free bit vectors benchmarks, is really increases 11-fold between 2010 and 2017. These are fantastic improvements, which continue getting better and better every year, is the key to success in logic-based verification. Very complex program verification tasks could be actually now delegated to the solver. So the solver will be able to find the problem solutions efficiently. Yes, they all will be complete problems, and they really not always produce the solutions efficiently. However, this is the class of problems which witness the fact that many problems could be indeed solved efficiently. We are using this approach, logic-based approach, and we are using SAT solvers and SMT solvers in our tools. Our approach, the source code is given to a model checker, which is tightly coupled with the SAT or SMT solver. So there is an encoding task inside of representing program model together with specifications as a logical formula, and then the formula is given to the solver, and solver produces a result which corresponds to the verification result being verified with successfully, meaning that the properties which have been investigated hold, or unsuccessfully, meaning that the properties fail. And in this case, the SAT solver produces the counterexample, the witness to the bug. Boolean and SMT encoding. I'm quite sure most of you really know. I will very briefly go over it and then go to demonstrate how it's used in bounded model checking. Here's an example of a Boolean encoding for tie and short example. And the construction is a formula in a conjunctive normal form where each variable is a Boolean variable. The question is the formula satisfiable or not? And here on the right, you can see this is a satisfying assignment to this formula. Satisfiability modulo theory, it's a very similar concept. It's based on Boolean satisfiability together with an addition of decidable first-order logic theories. Here's some example, and where you can see the use of uninterpreted functions and linear arithmetic. And as you can see, based on this example, this formula would be unsatisfiable. It's impossible to find a satisfying assignment which would turn this formula to true. How does it work in the area of program verification? Let's look at this simple example and let's see how it could be encoded into SMT formula. Each line represents just particular statements of the program or assignments, and all of them could be encoded as the clauses of the logical formula, SMT formula in this case. And as you can see, under these conditions, with these particular values, this formula cannot be satisfied. But if we, for example, drop the fact that x gets assigned to 1, meaning that the clause x equal to 1 disappears from the formula description, then the formula can be sat. This is just an illustration of logical encoding of a program into a formula. And formula is then being solved. And the solver behind encoding for each corresponding logic is going to produce a model, a satisfying assignment if it exists. SMT-bounded model checking. This example, for example, now has an assertion. This is a representation of a program property. This property is a safety property. We want to make sure that variable x is always bigger or equal to variable y. So how could we verify this property? Let's do the symbolic encoding first. The very first step is to perform a single static assignment encoding, which clearly separates all assignments, all updates of the program variables, and you choose some initial bound, for example, bound y for the loop while in your program, and this is the single static assignment form for this within this bound. If the bound is increased to 2, then this is how the encoding changes, and we can continue for a while by increasing the bound, trying to unroll the loop as deep as possible and to see if there is a bug within this depth. These assignments then are used to create logical formulas representing the problem behavior. This formula, which now we can construct, is really extracted from a single assignment form. And from the formula, each assignment of the variables used in the formula, such that they satisfy the formula, they represent a particular behavior of the program. It's an execution path, starting from the initial values of the program up to the values of the program corresponding to the bound at which we are looking. This illustrates how we could encode program written in a favorite programming language into a logical formula, which then used in the past to solver to be examined and see if it's sat or unsat. This is the concept of bounded model checking. This is a very popular approach in program verification. Let me very briefly to explain it, because the tools I'm going to present later, HyProg and UpProg, really based on this concept, and I would like to make sure everybody is clear with how it works. We unwind the program model up to a particular bound, to a particular depth. For k levels, we construct all computations of length k, all possible behaviors of the system will be encoded up to this particular bound. While doing this unwinding and encoding, we will see if ever this property which we are trying to verify is going to be violated or not. How we are going to do it? We are negating our property. For example, our task is to verify safety property. It's always global as a fact that proposition P holds. If it's the negation of this property would be the evidence of the bug. The not P, if you ever encounter an P, it means the property is violated. And then we will produce a counterexample, which will witness how we can get from the initial state of the system to the buggy state. If we never encounter the fact that not P is reached, then we increase the depth and keep going, trying to verify that the system is safe as deep as we can go. This is the encoding. We first start from the very beginning, from the initial set of states, and we see if for these initial states and initial values of the program variables used there, we ever reach the error state. If we don't, we add the next round of depth. We'll adding the transitions, which corresponds to the update of the program variables by one single step. And again, we see if the buggy state is reached. It continues. We unwind and we increase in the bound up to K level. Let's say this is the level we choose for we believe is sufficient for verification of our program. This is the formula. It could be very large because value K could be very large as well. And this is the logical formula which is then passed to the solver to see if it's satisfying or not. If this formula is satisfiable, it corresponds to the fact that the system is buggy. It means that the error state is reachable. But if it's unsatisfiable, it means that the state representing the error state is not reachable. The solver, which is going to solve this formula, is going to give you a verification result. See if your system is safe or not. Logically speaking, we constructed a formula for SAT or SMT. First, we have a formula describing all possible computations of the program up to depth length. Then we construct a formula expressing the bug, the violation of the property we are checking. We conjunct them together into a single property, and this property is then given to a solver. If the formula is satisfiable, then the system has a bug. So the property is violated. It does not hold. As a satisfying assignment which a solver produces is a counterexample. It's quite efficient and it's quite convenient to do this. And as I said, the solvers which do the solving, trying to find a satisfying assignment, are extremely efficient these days. You can construct formulas consisting of millions of variables and clauses, and the solver might solve the problem within milliseconds. That's the overview. This is what symbolic model checking is about, using SAT-based approach. Really relies on the SAT solver as the computational engine of the model checker. Our tools using this approach: symbolic bounded model checking. SAT-based model checking was the original approach from late 90s, introduced by Ernie Beer and his colleagues, and it was demonstrated to be an excellent tool for many problem domains, and really relies on the fact that extremely efficient SAT solvers exist. However, because it requires bit-level encoding, propositional logic encoding, we end up with very large formulas, sometimes so large that even efficient solvers cannot handle it. Search space, which has to be explored, is enormous. Sometimes it even prevents termination of bounded model checking. We can really easily see that this is, despite of the evident advantages of using SAT solvers, it's still a very expensive approach. For this reason, SMT has recently become very popular. SMT encoding, while taking all the advantages of SAT solving based on same decision procedures for propositional logic reasoning, it also allows to add first-order logic encodings. The first-order logics are more expressive and they are more compact, so they're more natural to correspond to the program constructs which we are using in the program descriptions. Here is an example of such a program. As you can see, it doesn't seem to be very complicated, though it operates within a large bound of values of variable n. If it would be bit blasted, encoded into SAT, then roughly speaking, here's an estimate which my students did. It's like more than 4,000 lines of encoding, which would we see on the screen. However, if you would use first-order logic encodings, as it's demonstrated here on the slide, you can see the formula is fantastically short and not looking complicated. And for SMT solving, definitely there are also very nice and efficient solving procedures which could be employed to solve SMT formulas with the same aim as in SAT solving, in SAT-based verification, trying to find the verification conditions satisfied or not. There are different, first of the logic theories. They all quite nicely applicable to program modeling and consequent verification. For example, one of very popular theories is equality logic and uninterpreted functions, EUF. Here's an example of using uninterpreted functions, and there are very efficient decision procedures for this logic and for this theory, and can be nicely employed. Here's another example, linear real arithmetic theory or theory of bit vectors. As you can see, it gets gradually, even in my examples, from something trivial to something very complex. And complex theories, complex operations imply that the decision procedures which exist for solving also require a lot of computational resources. They are less efficient, they are expensive. The idea in employing SMT solving in program verification is to try to find a trade-off between expensive and non-expensive procedures such that it still works appropriately for the program verification tasks. The focus of our presentation is SMT-streamlined model checking. The tools which I'm going to present later, HiFrog and Approve as well, they're all SMT-based. It's bounded model checking with the employment of SMT solvers. And the procedure, as I showed it for SAT-based encoding and verification, the only difference is that we are now using SMT-level encoding and SMT solving. And whenever SMT solver returns SAT to a verification of the system, it means the system is buggy. It reports a counterexample, and we have a violation of the system property. However, if it's unsat, we know that the system is safe and the property has been satisfied. In our projects, we have SMT encoder. This is like a preprocessing step for all our program verification tools. Performs this single static assignment slicing, as I showed you earlier in the example, by parsing the input code of the given program, and then it's possible to encode it in different logical encodings. We are using EUF theory, linear real arithmetic, linear integer arithmetic, theory of bit vectors. Well, and of course, we keep the propositional logic encoding. Naturally, the level of abstraction goes from being very precise to being very abstract. The propositional logic is the most precise encoding of the program. It's also very expensive because it's the very large size of the formulas we have to verify if we did last in the code. On the other side of this encoding, so we have a lot of cheap procedures, computationally efficient procedures, if we're able to encode the problems into uninterpreted functions inequality. However, the precision suffers. This is a very high level of abstraction, might lose some important details, which we would have to somehow bring back if they are important for verification of the properties which are given to us to analyze. One of the interesting aspects of our tools, of our SMT-based verification, is trying to find the trade-off between level of abstraction and precision. So it's a key factor for success to find the right level that is sufficiently precise and not too expensive to reason on. And it depends on the program. It depends on the domain of the problem you're analyzing. It's impossible to decide it a priori. The tool somehow, incrementally, as you might guess, as it happens in our projects, identifies this appropriate level and finds this trade-off between the precision and the efficiency of the procedures. I will finish my first part with a short demo of Our tool Hyfrog, which will contrast SMT-based reasoning against SAT-based reasoning, SAT-based BMC and SMT-based BMC, we will immediately see a difference which SMT highlights. So SMT encoding is really, really much better instrument to achieve a better efficiency. Here's a short demo which illustrates that, for example, we can use uninterpreted functions for program encoding. Let's take some program to analyze. Here's the source code of the system. And this example actually uses non-linearity. Technically speaking, it could be very expensive. And in this particular example, we see that LRA use is actually not necessary, so you can really verify the correctness of the program even if it's interpreted in using uninterpreted functions, because the program does not depend on the exact interpretation of the multiplication, the operation used in the example. In fact, it suffices to assume that the function returns the same value when invoked with the same parameters. This an example, and you can see here that the property we are verifying, indicated by the word assert, is to check if variable p is equal to variable q. We are going to take this program, C program, and verify it using SMT-based approach, using uninterpreted functions encoding. And plain 1 corresponds to the assertion, property number 1, which we are verifying. As you can see, it's done. I already ran the tool, and the tool told me that the verification was successful, and the amount of time it took to verify was really negligible. It's really very efficient verification. You might say, why I'm showing it to you? Seems like such a trivial example. But what I really want to illustrate, if I will try to verify exactly this code with it blasting, with using this same property, but using SAT-based approach, some things which I really we would not like to see will happen. And this is what exactly happening now. Our OpenSMT tool, which is run as a SAT solver in the propositional level, started computing, started trying to do the computational tasks of verification, and it just keeps going. The amount of memory it takes keeps going. It just takes too long. And what's going to happen? It's what usually happens. We simply kill this effort, and we cannot use it anymore. With this, I will conclude my part 1, and later we will move on and try to understand what is this function summaries and why is it so useful in program verification.